Okay, cool. Happy Monday, everyone. Anybody have any questions about anything before we start? Okay, so this is where we left off last time. So we're still in chemical accounting. So we're trying to figure out, kind of general idea at this point in time, the amount of things, how much we can make, these types of questions. And we were introduced the idea of theoretical yield, meaning how much can I actually get from something. So we started off with theoretical yields where you knew what the limiting reagent was. So reactions go until they're limited by something, and that reactant is called the limiting reagent that you're limited by. If you're driving your car, you're worried about when you're going to run out of fuel. Your fuel is your limiting reagent, not the amount of oxygen in the atmosphere. But now we got these cases where we don't know what the limiting reagent is, and here's one. We start off with 86.3 grams of hydrogen monoxide, 25.6 grams of hydrogen, and we have to figure out what the limiting reagent is. You go through the analysis and you pick the one that has the lowest amount of product. And some of the new concepts are, in this step here for both, it's comparing the ratios between reactants and products, or any species really, in the balanced chemical equation. So the chemical equation needs to be properly balanced to get those proper ratios. And then so that's this step here. And then by dimensional analysis, we find we get about 50 grams of ammonia. The other one we get about 90 grams of ammonia. You pick the lower one. 48.9 grams of ammonia is the theoretical yield, and that's based off of this limiting reagent here. So we left off was here, and I wanted you guys to work on this. So we didn't get a chance to go through this all the way, and this is an important concept. So I'm going to spend more time on it. 100 grams of oxygen, 100 grams of hydrogen react. How much water will form? What's the theoretical yield from this reaction? And here are some hints that there's the balanced chemical equation. 2 hydrogens plus oxygen makes 2 waters. The molecular weight of hydrogen is 2 grams per mole, oxygen is 32 grams per mole, water is 18 grams per mole, and there is hydrogens right there. So I went ahead and put out the analysis there for hydrogen. So now, why don't you try it for oxygen? Some people are squinting. Is that hard to see? Raise your hand if you can't see it. Okay.
There's some glare on the right side of the screen, at least for...
Oh, really? Oh, I see what you're saying.
Some of the smaller.
Okay. Which ones?
Gallons per mole. H2O,
yeah.
18 gallons per something.
18 grams. Okay, well, I'll tell you what I'll do. Let me copy this and put it here, and let me zoom in. Oh, too far. Is that better? Anybody stuck? Raise your hand. We'll go ahead and break up into groups if you wish. Usually I'll come this way now just to switch things up. All right. go through the balance equation. So it's going to be mole oxygen there, 2 moles. Get that from the balance equation. Yes, that's fine. No worries. No, this is important that you get this.
So I mean, I understand what we're trying to do, but I just don't understand what we're trying. So,
Which number do you
well, I know where to.
So this is my few moles of oxygen.
Understood that.
And then, okay, so this is a 2-part water to 1 part oxygen. So I put it here. So a mole is 1 there and 2 there.
Oh, now I understand.
The person has 2 hands and 1 head, right? So
Yeah.
2
Grams.
Yeah. Yeah.
Okay.
And now you see that this energy here is grams.
Yeah, I understand.
Yeah, just like how the hell do I get that? So, okay. No, it's good that you're in your class.
Exactly, right. Is that what, okay, so, yeah. I can't reverse engineer math.
You got it? Okay. You got it? Got it. Okay, cool. That's the right fraction. good. Same thing. How are you doing?
Not
Not well?
well. No,
Is this in general or just in chemistry?
in chemistry.
Okay.
I don't understand. I don't
Okay.
understand the equations and conversions, and I can do all my homework, but then when it gets to the conversions, I can't do it.
Okay, which ones are you getting stuck on?
All of them.
All of it? Okay.
I just don't understand what they're asking and how to get there.
Okay.
So,
No worries. I mean, so, I'm sorry if I sound like a broken record. It's just, I mean, you look at a problem. So 100 grams hydrogen, 100 grams hydrogen, 100 grams oxygen react. How much water will form? So you want to know how much water is forming.
right.
And given information, given a balanced chemical equation, I also gave you the molecular masses.
Okay, so here's your given information. That's, okay.
And
They're telling you this,
Yeah.
they're giving you something to work with. So
yeah,
in English, not numbers, in English, how do you explain what you do with this? You multiply what by what to get what? Like what would English be?
English. So I mean, I can explain the math in English. I analyze it
I
mathematically.
understand.
But
Can you explain the math in English?
sure.
Okay.
So let's start off with 100 grams. So when I start with 100 grams of hydrogen, so I start with both reactants. I did calculate out what the theoretical yield is for both hydrogen and oxygen to determine the limiting reagent. So I start with 100 grams of hydrogen. I figure out the number of moles of hydrogen by multiplying or dividing by the molecular weight. And then I look for the ratio between hydrogen and water.
We're going to figure out the moles by multiplying the
Well,
molecular
dividing,
weight.
in this case, dividing.
Okay.
And now we have to get the ratio between water and hydrogen.
Mm-hmm.
And once we figure out the number of moles of water, we multiply by the molecular weight of water to get the mass of water.
One more time. Now we've got the ratio.
The ratio, and then to get the mass of water, multiply by
Mm-hmm.
the molecular weight of water.
Did they already give us that?
Yeah, well, I did. I originally started off by not providing that information, but I wrote this problem. It's a very short problem.
Oh, that's very cool. Okay. So we start out, we're always going to start out, we want to convert grams to moles.
I mean, depends on the problem. I mean, the thing is, there's an infinite number of problems. There's not really, like, there's not one equation that's going to fit for everything.
Okay.
There's not one way of doing things. You have to think through every problem,
Mm-hmm.
unfortunately.
Well, no, I mean, that's just the way it is. It is what it is. So figure out moles by dividing the molecular weight. Now we get the ratio.
Yeah, for the balance equation.
From here.
Yeah.
Ratio.
And it's 2 to 2 or 1 to 1, however you want to put it. I put 2 to 2 just to make it, because students are confused.
Okay. So now we've got the ratio, and that is, where would the ratio be in here?
It's in the balance equation. It's here to here for hydrogen, here to here for oxygen.
And what did you say it is?
For which one?
Um,
Hydrogen? Hydrogen to water, it's 2 to 2 or 1 to 1.
two,
Because it's a 2. 2 to here, 2 to here.
and 2 to 1. Is that correct?
2 to 2, and well, it's 1 oxygen and 2 waters, so it'd be 1 to 2.
This one is 1 to 2.
This one to that one is 1 to 2, because there's a 1 implied here.
Okay. I'm sorry. Just,
Okay. It's like, think of it like 2 hands, 1 head.
Mhm.
Right? Each person has 2. Well, most people have 2 hands and 1 head.
Some
Right.
people have 2 heads, I swear to
Well,
God.
okay, well, perhaps.
Most of them drive around in haiku.
Okay. Yeah. So avoiding haiku. 2 hands, 1 head. Right. So I mean the ratio, like you're dealing with ratios of whole numbers like that, and it's always going to be, I don't know, maybe 2 hands to 1 head to 2 feet or something. I don't know.
Okay.
So
Well, just so that I don't confuse myself, what is the proper way to write this?
what do you mean by proper?
Well, like I wrote ratio 2 to 2 and ratio 2 to 1, and that's not right.
It's, well, just because this is further left, I would put 1 to 2.
Where?
1 oxygen, 2 waters. Depends on what species you're talking about.
Okay, I'm just going to cross this out because I'm going to confuse myself by looking at the wrong thing.
I mean, it's like a ratio is just, it depends on what you mean. Like my ratio of hands to heads is 2 to 1,
Mm-hmm.
and my ratio of heads to hands is 1 to 2.
Mm-hmm.
Right? So it just
Right.
depends on which order you're looking at.
Right. Well, so to get mass, we multiply it by the molecular weight of water.
Mhm.
And is there anything else that?
No, that's it.
And that's it. And then now this is back in grams.
Yeah.
But how did we end up back in grams for moles?
So if you look at this, grams hydrogens cancel. So
Mhm.
grams hydrogen, moles hydrogen, moles water, and you're left with grams. That's called dimensional analysis.
And is that going to be true in every dimensional
Yes.
analysis?
Assuming you get the right ratio.
We found a constant. Cancel out moles in equation. Cancel.
Yeah, I mean, notice that each time that you have here on the left is on the denominator, so the units all cancel with those friends.
Mm-hmm. Okay. And then this whole thing is called the dimensional analysis.
Well, this process is called dimensional analysis.
All of this, or just this canceling things out?
Canceling things out is called dimensional
Thank
analysis.
you. Yay. Thank you. You don't want to take up all your class time. Thank you.
You got it? Okay. Okay, going around, it looks like people are starting to converge. And just to explain again, so 100 grams oxygen, 100 grams hydrogen. So for oxygen, mole of oxygen is 32 grams per mole. And then the next step, we look at the balanced chemical equation. And there's 2 moles of water for every 1 mole of oxygen. And then 18 grams per mole water. And we get 112.5 grams water using hydrogen. Start with 100 grams, divide by the molecular weight. Here it's a 2 to 2 or 1 to 1 ratio. And then same 18 grams per mole water, we get 900 grams water. So which one is the right one? You pick the lower one, 112.5. The other thing, notice 900 grams is definitely not right because you start with 200 grams of reactants. How can you start with 200 grams of reactants to get 900 grams of products? So that's one of those check your answer things. And looking at this, you could probably guess that A or B is the only proper answer for this. Because even that, you could probably even deduce B is the only proper answer. 900 is out because it breaks the conservation of mass. And then you start with 100 grams of reactant of each. And your product, there's only 2 reactants, and your product has both of the reactants in there. So you know you're going to go greater than 100. You have the same 100 for both. So you know your value is going to be greater than 100. It's unlikely that it would react completely to its completion just by that. But it's a viable answer. But just by looking at it, B is probably the right answer if you're giving no time to work the problem. So, questions with this? Okay. So the next concept is actual yield or percent yield. So the percent yield is your actual yield over your theoretical yield times 100%. So, and why would you not get 100% each and every time? So what is it? Why can't I get 100% each and every time? The reason is because things are not pure. So this next problem we're going to talk about deals with cracking ore. And this is how we crack ore. So how much titanium can we get from its oxide by this equation here? So we have titanium dioxide plus 2 carbons makes titanium metal and 2 carbon monoxides. And lo and behold, this is how we get most metals. So most metals we get by taking ore. Ore is a rock that has the metal in it. And then we reduce it typically with carbon. So this is how we get pretty much every metal except for aluminum and gold and platinum and some of the side products from platinum like palladium and rhodium. So that's leftover stuff from platinum development. But every other metal we get by reducing with carbon. And if you look throughout history, we've done this. Some of the easiest metals, you can get copper and lead. You can get that just by using campfires. So if you get copper ore or lead ore, galena is lead ore. This is important during the colonization of the United States, for instance. When settlers would find galena, so it's really pretty rock. It's black and shiny. They would collect it, and then they would throw it in their campfire. So you had the campfire, and then they would throw the galena into the campfire, and then the heat from the campfire and the carbon from the coals could reduce the lead, and you would get lead left over. And they would sift through the campfire ashes, get slugs of lead. You could melt it down to make musket balls, and that's how they got their ammo. And then if you had gunpowder, then you could, if you ever played Oregon Trail, right, you can go and shoot the buffalo with your bullets. So you can if you want to. I mean, now of course we've stripped pretty much all of the surface ores. So some people think that we had advanced civilizations before us. It's unlikely that we've had advanced civilizations before us, at least in the past several tens of millions of years, because we've taken all of the easy ores, like some stuff at the surface. So unless the previous advanced civilizations did not require the use of metallurgy, which I'm pretty sure they did, we're the only ones that have developed it, at least to massive scale. So, but I always liked it. I've been watching those Ancient Aliens. It's on Netflix now. It's so stupid. I love it. But okay, so this is also how we get iron. Of a really important metal is iron. And the way you make iron is use a blast furnace. So blast furnace means you blast in oxygen. And in the top, you put carbon, iron ore, Fe2, Fe2O3, magnetite, hematite, and then you also put lime. You put calcium oxide. And you blast it with oxygen, and what happens is the carbon reduces the iron, and then you get this layer that floats on the top. The layer that floats on the top is called slag, and the slag is magnesium and calcium silicates typically. It floats. And then you have the iron comes out on the bottom in a liquid, and I'll even draw it red. And does anybody know what pure iron is typically referred to as? It's called pig iron. And the reason why it's called pig iron is that they would draw it out of the blast furnace into a channel, and that would form bars. And you would have the bars, it would just by flowing. And this was back in the 1850s-ish when we started doing this in massive scale, 1850s to 1900s. And this was during the Industrial Revolution when people left the farm and came to the cities to work. And people were like, oh, that looks like a bunch of piglets suckling on their mother. So the bars of iron coming off. I mean, cats are the same way, right? So humans were different. We only have 2 nipples, right? So other animals have a whole nipple line, and they have bigger litters than we do. So then you have the dogs, cats, pigs, same way. So that's where it came from, pig iron. It's a farmer's metaphor, really. And but I mean, that's how we get most metals. Like I said, aluminum is different. We use cryolite and bauxite. That's that's aluminum oxide and aluminum fluoride, and you combine that with carbon rods and electricity, and then that forms molten aluminum. So we use electricity to form aluminum rather than just straight heat and oxygen. Gold, we get it a couple ways. You can find it just in its native form. That's one way you can do it. You can take mud, like in rivers that are really thick in gold, and you can pour mercury into it. And then you can take that mercury will absorb all the gold, and you can take the mercury out and you can hit it with a blowtorch. You boil off all the mercury, you're left with gold. That's what they do in the Amazon. It's really damaging to the Amazon. There's mercury polluting the Amazon River, for instance. That's a bad idea. What we do in the United States is we find gold-rich rocks. We grind them down, and then we mix it with cyanide. We let it sit in cyanide, and then we take the cyanide and we reduce that to gold. So the cyanide will dissolve the gold. And we do that similar process for platinum. And platinum has excess palladium and rhodium, and that's where we get our palladium and rhodium from as well. So it's just leftovers from platinum. We're usually looking for platinum and we get added stuff, extra palladium and rhodium from that. But every other metal, titanium, copper, lead, zinc, all these, we do it by heat it up in the presence of carbon. So, and if you look at this, so look at the numbers here. 28.6 kilograms of carbon, 88.2 kilograms of titanium dioxide, also known as rutile, 42.8 kilograms of titanium is produced. So that's not an industrial scale. So maybe if it was 1,000 tons, if it was 28,000 tons of kilograms of carbon reacts with 88,000 tons of titanium dioxide. This would be too small. You would go out of business if you're only making 40 kilograms of titanium. So what this is referred to as a pilot plant. So a pilot plant is somewhere in between a batch reactor and this full industrial scale-up. So what do I mean by that? Say you're making cookies. Have you guys ever made cookies at home? I have. How do you do it? You take your bowl, you put in your ingredients, you mix it in the bowl, then you put it in the oven, like you make little balls of cookies and you throw it in the oven. When that's open, you take it out, you put the next one in, you do that way. That's the way you make cookies. Is that the way that Kraft makes cookies when they make 100,000 cookies an hour in their factories? No, right? You're gonna have this big mixing tank that throws in the ingredients and mixes up. You probably have like some sort of extruding sort of thing that pushes the slurry batter into these little things. And you probably have sheets of it that run over like a lamp, just a really heating lamp. And in the end, the cookies come off and then they're put in through automated lines to the packaging materials. That's the full-scale industrial scale-up. So, but there's an in-between step, right? I mean, making cookies 10,000 at a time in an hour is different than making cookies in your kitchen. I mean, you get the same product, but there's a difference in how you make it. And when you do the scale up, once you get the recipe, let's say that they're going to change the Girl Scout cookies. I like Girl Scout cookies. Let's say they change the recipe, right? And what's going to happen if they use the same process? They're going to burn a bunch of cookies, right? The cookies are all going to get burnt because it can't be the exact same thing. You have to optimize the process. So what they do when they optimize a process, they use a smaller automated system called a pilot plant. And that's what this is. It's kind of like the donut machine if you go to Krispy Kreme. You've seen the donut machine there. That's a pilot plant. I mean, I know that's what they make for the Maui, but I mean, you know, it's if it was the like scaled up to for the United States, it wouldn't be, it would be much bigger than that, but it would be similar automation. So this is the pilot plant, and it's, I mean, it's more than just cookies, right? This is also how we get pharmaceuticals. So we discover certain drugs. The chemists come out, find natural products, or try a different combination, make drugs. You can make drugs in the laboratory. Then they make a bunch of the drugs, and then they say, okay, well, it looks like this drug is going to solve this problem. Like, okay, and then they get it through the FDA. They're like, okay, now we figured out how to make it in the laboratory. How do we make many of these drugs so that we can mass produce it and send it out and distribute it to everyone? You have to go through something like this, the scale up and then mass production. So, okay. But let's go ahead and do this problem. So this is the same thing as we had before. We have two reactants. We have carbon and titanium dioxide ore. And so we have to figure out what the limiting reagent is. And then we have to figure out the theoretical yield. So let's go ahead and figure that out. And let me change colors. So we have 28.6 kilograms carbon and 88.2 kilograms titanium dioxide. Okay, so same idea as we've been following along. So mole carbon to 12.01 grams carbon, or 12 grams, whatever you want to put. And then we look at the balance equation. We have, oh, I guess I'm skipping a step. So 1,000 grams carbon to kilogram carbon. Sorry about missing that step there. In my mind, I know I have to divide by it, so I kind of in my mind, I already discounted that step, but I'll show you. Mole titanium to 2 moles carbon. And I'm getting that from the balanced chemical equation. There's a 2 in front of carbon, and there's a 1 implied in front of titanium. And then the molecular weight of titanium is 47.87. 47.87 grams titanium per mole titanium. And where am I getting that from? I'm getting that from the bottom number of the periodic table for titanium. So let me go to my periodic table. You can't really see, but here's titanium. Titanium is here, and this says 47.9. The other one says, the textbook says 47.87. But the number right here underneath titanium is where you get that number from. So, and then the last step is kilogram titanium to 1,000 grams titanium. So you can see the thousands cancel anyways. Same thing with the rutile, with the titanium dioxide. So 1,000 grams titanium dioxide to a kilogram titanium dioxide. Mole titanium dioxide to 79.87 grams titanium dioxide. And that step is titanium plus 2 times oxygen. Oxygen is 16, so 47.87 plus 16 times 2. And then we have mole titanium to mole titanium dioxide, and then 47.87 grams titanium to mole titanium, and then kilogram titanium to 1,000 grams titanium. Okay, so the book does not carry it all out. I will do that real fast using my free calculator. How many ads am I going to get today? Okay, 28.6 divided by 12.01 divided by 2 times 47.87, and this is 56. Oh, there's my ad. Ooh, news break. Maui County News. Oh, it's just 57. This is 57.0 kilograms titanium. And the other one is 88.2 divided by 79.87 times 47.87 and 52.9. How many kilograms titanium? So which one is the theoretical yield? It's this one. 52.9 is lower. And then our percent yield is our actual. So, it's our actual yield is given to us, 42.8 kilogram titanium all over 52.9 kilogram titanium. And looking at this, we then get 80.9%. Okay. So once again, figure out what the limiting reagent and theoretical yield is by looking at both reactants, and we find out that we get the limiting reagent is the ore, and the theoretical yield is 52.9 kilograms titanium. We're given that we get 42.8, and that means our theoretical yield is 80.9%. So our actual yield over our theoretical yield, and we get 81% theoretical yield or percent yield. So why is it not 100%? Because this is a rock we dig up from the ground. Okay, it's going to have dirt on it. It's going to have other things. It's going to get some random sulfur atoms in there, and like everywhere on Earth, it's probably going to have calcium, magnesium silicates, which are also known as slag when you rip it out. So if you ever seen like the movies where they're making swords, they have like the blacksmiths are there and they're hammering. You see these sparks flying everywhere. Those sparks, that's slag. Okay, that's calcium, magnesium, silicate impurity. So the slag, you can hammer it out with your hands, or you can throw it in a blast furnace and throw some lime in there and heat the heck out of it, blast some oxygen into it, and then it'll float on the surface. So whichever one you want better. It's of course it's much more rapid to do it in a blast furnace than it is, with your muscles. Okay, so that's why we don't get 100% yield because of the impurities. Sometimes, though, when you're in chem lab, you might find out that you get a greater than 100% yield. So just like my football coach would say, you got to give 110%, you can actually give 110% in lab. But in that case, it's because you didn't properly dry your sample. So a lot of times you'll have like a precipitate come out and then you weigh it. Well, you should dry it off first, because if it's not dried completely, you can give 110% and make my football coach really happy, right? So that's one thing to watch out for in practice. So you might see in practice you get above 100% yield, and that's just an artifact of your experimentation and not necessarily doing it properly. If you do everything properly and you can capture every single atom, you should get 100% yield each and every time. You have a question, or?
Actually, sure. I just have a quick math question.
Yeah.
On the second one, the 88.2.
Yeah.
By the time you got to 79.87, you were dividing, not multiplying. I just wondered what happened as you were working your equation.
Okay. So you're given a mass of a reactant, and you have to convert the mass of reactants to moles of reactants. And now we're going to convert the moles of reactant to mole of product in this step, and then we convert back to mass.
Right.
Yeah.
But you're multiplying all the way across, and when you got to the second part of that, you divided by 79.87.
Yeah.
So why? Why did you divide instead of multiply?
So if you look at the units, this is kilograms cancel, the grams cancel, and then the moles. It's the way the dimensional analysis, the units. You have to, when you design this problem and you design the solution to it, you have to make sure that you write this properly so that then one unit will cancel each time going across. Do you notice here that kilograms cancel, grams cancel, moles of that cancel?
Right.
Yeah.
But why did you divide instead of multiply? That's all I wondered.
Because the grams titanium dioxide are on the numerator, so you need to put grams titanium dioxide in the denominator.
Perfect. Thank you.
Okay. Other questions? Okay. Now let's say that you are a plant manager and this is your engineer and he or she is running the pilot plant, and then this is what the engineer shows you what happened. Is this a good result or is this a bad result? This is an amazing result. I would go and take the engineer out to lunch and try to promote that person. Because look what this engineer has done. What's going to be more expensive? Carbon, which is just get from, it's basically coal, or ore. Ore is much more expensive than coal. Coal is on the order of $50, $50 to $100 a ton. Okay, ore is much more expensive. I don't know how much titanium dioxide is. But I can guarantee you it's many more orders of magnitude more, probably on the order of 10 to 100 times more expensive than coal. So the engineer designed it so that the limiting reagent was the more expensive stuff. And it's also close, right? The person put enough carbon to ensure that I can get all the titanium out of this ore, but I'm not overloading it. So I'm being cautious in my cost of this. So I'm certainly having the carbon, the cheap stuff in excess, but it's not in a huge amount of excess. This is a moderate amount this is an acceptable risk. So if you're going to be managing something, what you do is you have to manage risk. This is a very good risk management, and this is a very cost-effective way to do it. So the risk is low, but I'm putting more carbon. It's cheap, but the benefit of that is I'm getting all the titanium that I can out of that ore. So, and then I get a percent yield, which, I mean, 80% is pretty good, actually, for percent yields. So this is a really good engineered problem. At least it's a good solution. So take the engineer out to lunch and try and promote that person. Tell that person doing a great job. Okay. So now your turn. 50 grams oxygen and 850 grams hydrogen react to make 50 grams of water. What is the approximate percent yield? So which one's the limiting reagent? Is it oxygen or hydrogen? Oxygen, yeah. So I made it obvious. Okay, let's. Just to drive the point home, I want to see if you guys can, if you look back, of course, you can divide the other number by 2. So your theoretical yield. It's 112.5 was the last one, so that's going to be 56.25. drive the point home. So how many people think A? How many think B? How many think C? And D? Okay, so people still need more time. Okay. Is anyone getting stuck? Okay. Okay, good. Okay, that's my answers.
Structure work out
How did what?
how you got that.
And the last answer was 112.5.
Okay, now I was looking at this.
Yeah, 112.5. So hydrogen is 1, oxygen is 16. 2 times 1 plus 16. So if you look at the periodic table, hydrogen says, this is what it says on, for hydrogen, oxygen is
So I did wrong. I got 1 and 2.
Okay.
30.
Okay, yeah, okay, you got it. Okay, so now you get the actual yield. Your actual and their theoretical yields. Your theoretical yield is 56.25. So you got that. So your actual yield is 50. So 50 56.25. Or your times 100. What are those? this one, what I'm actually the new thing is this. I mean, that's what I'm really after. That's why I'm kind of just giving you kind of feel because no, it's like this chapter. Well, there's concepts from chapter. The molecular weight. So this stuff. That's chapter 3. But I mean, when at a point, like, sometimes see if you understand this all the forms of assessment. Do you understand this now? You don't really understand it. How can I? The general idea is a strategy. So think of it as how games you're attacking the problem, you're attacking the tower or something. So how do you get to the solution? Well, you start off with the instinct and you just have to work your way up to the solution needs. And with maths and chemistry, you gotta go to moles. Okay. Oh, yeah, absolutely. You know, you can memorize the entire periodic table, but I got it now. Okay, yeah, I can go with it. Because it would be two. Well, I mean, this is two same things, so the answer. No. But I mean, yeah, I made this up. It's just too quick. I see your point. But I mean, I made this problem. It's just to check this. It's called formative assessment. It has a summative and evaluative. Yes. I understand what you're saying. Okay. Well, I mean, the important thing right now is you understand so the linear range stuff, though, it's like you need some more things. That's okay. Track this and then find out. Oh, you mean the mass launch? Yeah, you're correct. Well, the whole math, okay, the ratios, yeah, you have to get that from well, yeah, the same problem. That's just theoretical yield is your actual yield. So if you mix 50 grams of water, that's your actual yield. And what the yield should be, the theoretical yield is 50. This is the percentage. Yeah. Well, it's 88.88. I guess it'd be 89. Yeah. I mean, close enough. How you doing?
I just wondered, where did you get the 32 from? Is that from the atomic
O2?
mass?
O2 is so 2 times oxygen. Oxygen is 16.
Mm-hmm.
Yeah, 16 times 2.
Okay, and were we supposed to try and work the same thing for this?
Yeah, but if you do that, I mean, that's in such excess. The other thing is you had the previous problems,
Mm-hmm.
and you, if you look at the previous problem, you can just take the other one and sort of divide it by 2. But if you did the 850, so that would be 77,650 grams. So if you did it the other way, if you want to do it for that, you'll find out that you get 56.25 here and 7,650 grams using hydrogen.
And the figure that I would want for that, I would have to multiply 1.008
8 times 2.
times 2
Yeah.
to get that figure.
Yeah.
And the figure that I want to plug in here,
It's 2 to 2 or 1 to 1.
okay, so it's 18 grams up here, and I don't know where that's
That's water.
come from.
18 grams, 2 times 1 for hydrogen plus 16 times 1 for oxygen.
Okay, and to get the same thing here, I'm sorry, I need to go.
Moles, I can't see your moles. It's the same thing, 18 grams per mole.
Oh, it's the same thing.
Yeah.
Oh, okay, thank
Oh,
you.
wait. Mole hydrogen. Oh, and you need to have mole water down. Wait.
So that's where I need to multiply the 1.008 by 2.
Why are you doing a kilogram here? You don't need this thing.
Okay, it's because we did it in the
Yeah.
other one.
No, we only did it for that one. This is the only time we did kilograms.
Okay,
So mole H2 2 grams H2, and then you have a 2 to 2 ratio there, and then you don't need a kilogram, you need to have grams of water.
okay.
Practice, 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 unfortunately. Okay. So it looks like everyone's converging 90%, and some people are asking me about sig figs. I must admit, I made these problems, I made them really quickly, and just I didn't even really look at sig figs. So I wrote this problem here. And what this is, it's if you follow education theory, this is called a formative assessment. So on the fly as you're going assessment, and this is just feedback for me to see if you understand it. And then if you notice, like, where you guys are getting stuck, I'm trying to correct that as I go along, as I'm teaching this and as you're learning it. So this is the on-the-moment assessment. A test is known as a summative assessment. That's after the fact. So after you've learned it and then you take the test, like, okay, now I'm looking at it after you've gone ahead and done your learning. This is where you're at with your learning. So this is as you're learning it on the go. And I make these so that they're fast so I can assess a specific part of your learning. What I'm trying to assess here is if you understand the theoretical yield. Actual yield. So, questions? No? And we're going on to chapter 5. I don't know. how much time we're going to be able to go through this. We'll just probably start real briefly. So it's Monday, and it's Oktoberfest right now. Let's say I had a pint glass. I said, Mondays. And I slammed back a pint of good old Marzen beer. How many would be impressed by me slamming back a pint of Marzen? Oh, we got one person thinks it's impressive. What if I said, this is a particularly bad Monday. What if I filled up with vodka? Ooh. Now we got some takers.
Now that's impressive.
Yeah, why is vodka more impressive?
The proof.
Yeah,
Concentration.
more alcohol, more concentration. The concentration is greater, right? So, and concentration, and you probably know this already, concentration means amount per volume. So concentration is amount per volume, right? If you're like me and you like reading labels on things, you'll see a lot of times they say it's like lemon juice concentrate, orange juice concentrate. So what is orange juice concentrate? You can buy it at the store, right? What is orange juice concentrate? Well, it's a tube. In this tube of frozen orange juice goodness, that's the same amount of orangey goodness as in a pitcher of orange juice, right? You can take that tube of orange juice goodness, and it's concentrated. It has more stuff per volume. You can concentrate it further even if you want, right? You can if you want, you can get rid of all the water, and you essentially get tang. Well, the tang doesn't really taste like orange juice, though, at least to me. But it's concentrated. It's amount per volume. And we have some of these colloquial concentrations as well. And I'm doing this because alcohol is a legal beverage. You probably are familiar with the concentration term called proof. So what is proof? It's double the percent by volume. So the proof is the double percent by volume. So something is 40 proof. That means it's 20% alcohol by volume. Or many beverages, many spirits are 80 proof, and that means it's 40% by volume. By volume, I mean, if you have 100 milliliters, how you make 100 milliliters of vodka is you would take 40 milliliters of pure alcohol, and then you would take 60 milliliters of water, and you mix it together. Now you have, that's by volume. That's parts by volume. So, and like I said, when you have concentration there, we use this colloquially, parts per volume in alcoholic beverages. We have other parts. We have percent by mass as well. So, but chemistry is weird because and chemistry is not very, we're not very good at colloquial things. Colloquial meaning general population. Like this is, we don't talk about, gee, I wonder what the molarity of this drink is. No, you want to know its proof. But in chemistry class, we use molarity. And let's see here, how much time we have to go through this? I don't think we're going to have a lot of time. If you want to know where that came from, the proof, not the molarity. Molarity is just from moles per liter. But proof came from, in order for something to be considered whiskey, if you were buying whiskey, they still do it this way, the barrels. You have barrels of whiskey, and you're like, prove me it's whiskey. If you mix the whiskey with gunpowder, and if that catches on fire, it's whiskey. And then you have to pay the whiskey tax on that. So how do you prevent paying the whiskey tax? You mix water with it until it won't burn. And so there's a lot of whiskey that's got rejected, right, by adding more water to it. So that way you didn't get that way it avoided the whiskey tax. Also, if you study the way they make spirits, I'm just kind of, you can turn your brains off if you want. I'm just kind of filling in a little bit of time. Oh, you even put a pencil down. Like, yes! If you ever go to places like Ireland, Scotland, where they make Irish whiskey scotch, or the Bourbon Trail in Kentucky, the way they make whiskey is you take beer, you make usually corn, and you make beer and you distill that. You distill it 3 times to form something that's 120 proof. So 120 proof, which is 60% alcohol. That is sometimes referred to as moonshine, sometimes called Mountain Dew, sometimes called White Dog. White Dog because it packs a punch, or it packs a bite. So then they put that into oak barrels, and then they age it. And then typically you look for a place that actually has a seasonal change. Hawaii would not be a very good place to make whiskey because we don't have very much of a seasonal change. But then the flexing with the oak barrels, the seasonal change gets the flavors of the wood into the whiskey, and then you lose alcohol from that. So whiskey is typically so it starts off 60%. Usually it's somewhere between 40 and 45% ish. You lose alcohol. That loss of alcohol is referred to as the angel's share. So remember, this is very religious Irish and Scottish people, very very Catholic, typically, or at least used to be. And that was like, oh, we're losing alcohol, but it's the angel's share, so the angel gets some of it. So, but sorry for the colloquial stuff there. I was just trying to fill my time. We'll pick up here then on Wednesday, talking about concentration and other fun chemistry topics. Stay tuned for next Wednesday, or this Wednesday. Okay.